So here's another rational expression requiring a sketch from it. And the first thing I'll do is just factorise that denominator. That'll be useful for various things. So I've got x times x, it must be 1 times 2, it must be plus for the larger. That'll be useful for evaluating it, for finding the asymptotes, and in general just for finding the signs for various values of x. Well, sketch, so I'll start off with where does it cut the axis. So it cuts the y-axis if x is 0, and if x is 0, it's probably easier using this one, I've just got 3 over negative 2. That means y equals negative 3 upon 2. So there's the point 0, or we'll just call that negative 1.5. Why not? Where does it cut the x-axis? Well, that means that y would be 0. Now, if that expression is equal to 0, it's sufficient for the numerator to equal 0. So x plus 3 would equal 0, in which case x equals negative 3. So it crosses the x-axis at negative 3, 0. Next, asymptotes. I'll take the vertical ones first of all. I think I'll just abbreviate it. Vertical asymptote. So the vertical asymptotes will happen if the denominator can never equal 0. That means that x minus 1, x plus 2, does that ever equal 0? Of course it does. It equals 0, to put them in order, numerical order, at negative 2, or x equals 1. Better start highlighting some of this. So there's intersections with axis, and there's 2 vertical asymptotes. Now, how does it approach those asymptotes? That's where this expression will be useful now, just to see whether it goes to positive or negative infinity when I try and divide by numbers that give me 0 at the bottom. So let's take this one first. So as x approaches negative 2 from behind, what happens? Well, y is going to become, now, if x is negative 2, that top part will still be positive, that part will be negative. This is the only one that would become 0. This is the one that's sensitive to a slight change about negative 2. So if I go from negative 2, which is 0, and move it slightly negative, it's going to go negative. So go to that value, which is positive infinity. If I approach negative 2 from above, what will happen to y? Well, doesn't matter. At negative 2, that's positive. Change it a little bit, it's still positive. That won't change. Same with that. Negative 2, that's negative. Negative 3, change it a little, it's still negative. This is the only term that's sensitive to small changes in negative 2. If I make it go slightly positive, it'll go positive, in which case I've got negative infinity. So that means I could draw a picture over here. Here's my asymptote, vertical asymptote at negative 2. What happens? If I come up in it from the negative side, it's going to go off to the top. If I come back at it from the positive side, it's going to go off to the bottom. I'll do the same for 1. What happens as you approach 1? What happens to the value of this expression as you approach 1? Well, that's 4, and that'll always be 4-ish positive, no matter how I change that by small amounts, so that's positive. That's 3, and it'll stay positive no matter what I do. This is the sensitive term. If I'm at 1, it's 0. If I approach 1 from behind, then that's going to go negative, meaning it takes me to, it's really putting an arrow there, negative infinity. Let's really put arrows. If I approach the 1 from the front, what's going to happen to y? Well, this expression tells me. Again, that will be positive and that will be positive. That won't change for small variations about 1. This is the sensitive one. If I go positive, then that's going to go positive, which means it's going to head towards positive infinity. So at my asymptote, x equals 1, what's happening is, as I approach from behind, it drops down below. If I approach back from the front, it's going up above. Vertical asymptotes. Now, the non-vertical asymptotes, it's a proper fraction, so I can't express it in the terms of some part plus a remainder. So the non-vertical asymptotes, I'll just have to work with that expression the way it is just now. What would that become? Well, y equals x plus 3 over x squared plus x minus 2. What I can do is divide everything by x squared. 1 over x, 3 over x squared, 1 plus 1 over x minus 2 over x squared. And then, as x tends to infinity, that means that y is going to tend to, well, that will become 0, that becomes 0, 0, 0, it'll become 0 over 1, y tends to 0. So I've got y equals 0, in other words, the x-axis as a horizontal asymptote. But what happens at that asymptote? Well, that means I'll have to go back and consider signs, so I'll just have to consider it separately. What happens is x tends to, I should just put negative infinity there. Well, what have I got? y is going to tend to, what's that going to be? Well, that x is the dominant term on top, and that's going to be negative. That x squared is the dominant term below, and that's going to be positive. So that's going to tend to, if you like, it's just a small negative amount, or maybe since that's asymptotic, it's going to be 0 minus a small amount. As x tends to positive infinity, what's going to happen to y? Well, that's the dominant term, that'll be positive. That's the dominant term, that's positive. So it's going to come to a positive amount, so that must be some amount just above it. So for that asymptote then, for the asymptote y equals 0, as x tends to negative infinity, I'm coming up from below. And as it tends to positive infinity, I'm coming down from above. Next part's going to be any stationary points. I'll need to get the derivative. So that's that information, just put up here concisely, intersection with the axis, vertical asymptotes, non-vertical asymptote, and how it approaches them. Now the derivative. This is going to be a bit of a nuisance now, because I'm going to have to use the quotient rule here. I've got x squared plus x minus 2 squared. That's always very handy, because with a positive term, it means you can just ignore it in any signs. Then it's going to be differentiate at the top, that'll just be 1 times, unfortunately, this, minus x plus 3 times the derivative of that, which is 2x plus 1. So that's going to be still over that harmless entity at the bottom. So I'm going to have x squared plus x minus 2 minus, and that's going to be 2x squared plus 3 is 7x plus 3. Tidy that up. I'm going to have negative x squared minus that, minus 6x minus 5 over x squared plus x minus 2 squared. I think I might as well just factorise it while I'm at it. That's useful for various things. I'll take that negative out, and I'm left with, it'd have to be x, 1, 5, because that would end with the negative out, that'd be plus plus, so that's just going to be plus plus. So that would be the derivative, and factorised, ready to go. So there's a derivative of it. So if I'm looking for stationary points means that this derivative should be 0. So that's sufficient for this top part to equal 0. X plus 1 times x plus 5 should equal 0, which means x either equals, I'll put them in order, negative 5 or x equals negative 1. I'll need to find the corresponding y coordinates. Now I think for that I might use, what's different? Maybe for negative, I'll use this in both of them. So for negative 5 I'm going to have negative 5 plus 3 is negative 2, negative 5 minus 1 is negative 6, negative 5 plus 2 is negative 3, so that means y is going to be negative 1/9. So there's a stationary point at negative 5, negative 1/9, and if it's negative 1, that simply means I'm going to have a 2 over a negative 2 times a 1, which gives me a negative 1. So I've got a stationary point at negative 1, negative 1. There's my two stationary points. There's no horizontal points of inflection. There may be other points of inflection, but I'm not terribly inclined to find them and indicate them in the diagram. Equally, to justify the nature of these stationary points, I'm not going to use the second derivative because I don't want to go and differentiate that whole thing. It was bad enough doing just that one, never mind this one. So to justify them, I think I'll just use a table because I've got a nice factorisation here for it. So I'll use a table here, a table of signs. There's something at negative 5 and there's something at negative 1. I'll have to consider them separately because it's not a smooth function. I'll have to consider small steps in either side of each of them. But I've got fact now that's negative. I don't need to use it here for the equality, but when it comes to will the answer negative or positive, that's negative. So I think I'll put that negative, but my three factors would actually be a negative 1, an x plus 1 and an x plus 5 to give me my dy by dx. And then it's simply, that would always be negative no matter where. X plus 1, that's 0. Then, if it's less than 0, it'll be negative. Otherwise, beyond it is positive. That's 0 there. Negative before, positive after, so it must be positive all the way along there as well. So what happens at this one? I've got a negative, a 0 and a positive. So it's going down, along and up. So that's our minimum turning point. This one, I've got a positive, a 0 and a negative. So that's a maximum turning point. So maybe we could just put that in there. I've got a minimum at that and a maximum at that. And that's probably sufficient information now to draw the graph. There's no point working at the second derivative to find any lurking non-horizontal points of inflection. So, the sketch of it. Right, it's got a vertical asymptote at 1, x equals 1, there's a vertical asymptote at -2, x equals -2. I've not left myself enough room to get to -5 now. A horizontal one just on the x-axis, oh, y equals 0, I'll just put down there. It crosses the vertical axis at -1.5, let's just say that's about there. Crosses the x-axis at -3, somewhere about here. And it's got a turning point at 1, -1, -1, -1 being about here. And that one's at maximum, so I'll write it above it, -1, -1. And it's got another one, a minimum at -5. -5 and a tiny wee bit. I'll just put that about here. -5 and just -1/9. If you look at the back of the book, it says something like -0.5. That's wrong. The correct answer is -1/9. And it's just a case of snaking it all in between it, making sure it obeys all of these features, the way it approaches the asymptotes and the nature of the turning points. So what does that say? It should be heading off this way. From 1 it should be dropping down. There's nothing else happening there. So this should be just dropping down from here and becoming an asymptote to the x-axis. That's that part of it. This part before -1, it should be rising up to that turning point and then dropping down again, so that's fine. So it's going up to there and then falling down to here. This part's a bit more twisty because it should drop from here. In dropping from here, it's got to be an asymptote from below, and that's because it drops, takes a turn, and then a little twist, and then it heads along. That stays above it. That's the way the graph would look with its minimum turning point. Obviously, it must take a twist here somewhere, so somewhere about there will be some sort of point of inflection where it changes concavity from up to down. But that would be the graph. There it is for 5 part B.